As we continue on solving quadratic equations, we already talked about graphing in our last step, in step 10. However, now we want to learn 3 more algebraic methods for solving quadratic equations, and we will discuss when each method is appropriate to be used. One method is to solve by factoring. You may recall back in step 5 we practiced factoring. The only difference is now we have an expression set equal to 0, and that expression can be factored. If it's set equal to 0 and we get it into its factored form, that means we get it into 2 things multiplied together that equals 0. Well, if I tell you I'm thinking of 2 numbers that multiply together and give me 0, one of those numbers, maybe even both, have to equal 0. At least one must be 0 in order for 2 multiplied numbers to equal 0. So let's try to get this part on the left factored. To do that, we'll say, well, what do these 2 terms have in common? They both have a factor of 8, and they both have a factor of x. So when I factor this out, or you may think of it as undistributing, I would be left with 2x plus 1. And you can check by distributing to see if you get back to what we started with, and we do. Since I have 2 things multiplied together to equal 0, that means either 8x equals 0 or 2x plus 1 equals 0. Or quite possibly both of them equal 0. Solving the equation on the left by dividing by 8, I get that x would equal 0. Solving the equation on the right by subtracting 1 and then dividing by 2, I see that x is negative 1/2. These are both of my solutions, and if I check them by plugging them back through our original equation, you will get 0 for an answer. Sometimes all 3 terms will not have a common factor that we can factor out, a greatest common factor. This is a situation when we need to factor as if we were trying to do the opposite of foiling. In other words, what multiplies to give me 64 and combines to give me 16. That would be 8 and 8. 8 times 8 is 64, 8 plus 8 is 16. Again, setting each piece equal to 0 and solving, we get x equals negative 8, or solving the right side, x equals negative 8. So even without graphing, we know that this would just touch the axis at x equals negative 8. In fact, when we write our final answer, this is a little redundant. We would just say x equals negative 8. This next example is best suited for solving with the square root property. When you have a perfect square equal to some number, you can just take the square root of both sides. And when you take the square root of a number, you always say plus or minus 8. That's the fastest way to solve this. Another way, you could have set it equal to 0, because in order to solve with factoring, you must be equal to 0. And from here, I would say x plus 8 times x minus 8. If I FOIL or box these 2 terms, I would get x squared minus 64. And this would mean that x equals negative 8, and this would mean that x equals 8, which is the exact same thing we got initially, but I just wanted you to see the 2 different methods. Finally, sometimes we are going to have a leading coefficient other than 1. So here we would need to be finding factors of 484 that multiply to give me negative 44. Since 484 is such a large number, let's go ahead and use our calculator to help us find are factors of 484. And y equals, we're going to type 484 divided by x. Then, I don't really care what the graph looks like. I'm going to press second table, and you'll see all the possibilities listed out. So 1 and 484, 2 and 242, and so on. Remember, we're trying to get to negative 44, so both numbers must be negative. 3 doesn't work. 4 and negative 121. 5 doesn't work. 6, 7, 8, 9, 10, 11, and 44. And 22. And remember, once you find your winning combination, you can stop searching. Additionally, we also know that once we've made a continuous loop, we found all the factors. So negative 22 and negative 22 wins. We're going to place this underneath our leading coefficient accompanied with a factor of x. And we're going to reduce. Put it in lowest terms. So 2x minus 11 times 2x minus 11. Again, since this is the same factor, you don't need to solve it twice. You can simply solve it once. So again, we have a double root at 5.5, or 5.5. In a problem where they're asking how long an object thrown is in the air, using factoring will be very helpful because we simply want to set this equal to 0, this expression, because when this h of t is 0, that says that the height would be 0. That's what we're interested in figuring out. So let's try to solve this by factoring. Negative 16 times 5 makes negative 80. It's not too big, so let's go ahead and try to write out those factors. Negative 2 and 40, negative 4 and 20, negative 5 and 16. Remember, we're trying to come up with 79. If you're paying attention, you would have noticed we already had it with our first combination. So we're simply going to say negative 16t divided by negative 1, negative 16t divided by 80, and then we reduce. Right here, not much reduces except we can cancel the negatives. And right here, we're left with negative 1 over 5. So my factors become 16t plus 1, negative 1t plus 5. And if you FOIL it or box it, you will see that you get right back to negative 16t squared plus 79t plus 5. So setting each factor equal to 0 and solving by subtracting 1 and dividing by 16. Subtracting 5 and dividing by negative 1. And remember, t represents time in seconds. T is the time in seconds. So we do have two answers that solve this quadratic equation, but only one of them is reasonable. T equals 5. T equals negative 1/16 second doesn't even make sense with this situation. Time cannot be negative. Let's work backwards. What if I give you the roots and ask you to come up with the equation that would contain them. Well, we're just going to work this whole process upside down. We're going to start with our two roots. We're going to put them into factors and then multiply them to get our quadratic equation. So we'll start by saying x equals negative 1/3, or x equals 6. That's what we're given. But I want it to equal 0, so I'm going to add 1/3 to both sides of this equation, and I'm going to subtract 6. Then finally, I'm going to take these two factors, and I prefer using the box method. X plus 1/3, x minus 6, gives me x squared, 1/3 x, minus 6x, and finally minus 2. So this gives me x squared. Negative 6x would be the same as negative 18/3 plus 1/3, just because I don't feel like switching to my calculator. It gives me negative 17/3 x when I put these two terms together, minus 2. Now the only thing left, we want to multiply this entire equation by 3 so that we can cancel out this fraction. So we'll end up with 3x squared, take away 17x, minus 6 equals 0. In fact, just to practice solving by graphing, let's go ahead and type that into our calculator. 3x squared minus 17x minus 6, and then we'll graph, and it should cross at negative 1/3 and 6. And sure enough, it certainly looks like it does. We could again check it using our calculator's technology, but we're just trying to make sure our answer is correct and reasonable. The second part of this video focuses on completing the square. We're going to be talking a lot about perfect squares. And to start off, let's warm up by factoring 4 simple quadratics. This first one, I'm looking for two numbers that multiply to give me 9, but combine to give me negative 6. That would be negative 3 and negative 3, which I could write as x minus 3, the quantity squared. This next one, if you don't notice the pattern, just like we had in our first example, this first term is a perfect square, the last term is a perfect square, and the middle term is twice the product of their square roots. When that happens, we actually don't need to go to the trouble of saying 16 times 25, making a list of the factors and breaking it down. We can just apply our property that says write the square root of the first term, which would be 4b, the square root of the last term, which would be 5, and we want it to be negative. And there we have it. If I actually FOIL or box this, I'll get 16b squared minus 20b, which is minus 40b, plus 25. I could have done the same thing here. Write the square root of x squared, the square root of 9, keep the sign in the middle. Let's try the shortcut on this one. The square root of the first term would be 2x, the square root of the last term would be 1, keep the sign in the middle. If I multiply these, I get negative 2x, and double it, I get back to the middle term. So I know I've factored it correctly. How about this last one? Well, this last one doesn't fit the pattern because 3b squared is not a perfect square, and 3 is not a perfect square. But I can factor out a factor of a factor of 3 to start with. And now looking at what's left, b squared is a perfect square, 1 is a perfect square, keep the sign in the middle, and I factored it. This becomes really helpful when you have quadratic equations like this first example. We can take this entire expression on the left and rewrite it as x plus 5, the quantity squared. X plus 5 times x plus 5 gives me x squared plus 10x plus 25. Then, to solve this, to get rid of this square, I would take the square root of both sides, which gets me to my next step. Remember, when you take the square root of a number, you always put a plus or minus before it. I can simplify radical 49 to give me just 7. And then finally, I would subtract 5 from both sides to get negative 5 plus or minus 7. Well, you can't add and subtract at the same time. What this literally means is negative 5 plus 7 or negative 5 minus 7. Remember, with quadratics, we're expecting 2 answers. And sure enough, we get 2 answers. Let's try this one. Does the pattern hold? Is this a perfect square? Yes. Is 64 a perfect square? Sure is. Is negative 16x twice the product of their square roots? It is. So we could rewrite this x minus 8, the quantity squared. To get rid of the square root, I have to take a square root of both sides, always putting plus or minus before my number. The square root of 49 is just 7. Then I would add 8 to both sides. So my answer is 8 plus 7, or 8 minus 7. This is kind of the precursor to getting us ready to do the next method of solving quadratics, which is completing the square. If we can make a perfect square on one side of our equation, all we have to do to solve it is to take the square root. So that's precisely what we're going to do. But not all of these problems are going to work out as neatly as the first 2 examples have so far. Because of that, sometimes we have to make the square happen on our own by completing the square. This key concept does a nice job summarizing the steps, but it won't make a lot of sense until we try one as an example. For example, in our first term, x squared is a perfect square, but 12 is not a perfect square. So what I'm going to do, I'm going to sort my terms. If my terms have an x, they're going to stay on the left. But if my terms don't have an x, like negative 12, I'm going to add him to both sides to put my constant on the right. So terms with variables on the left, constants on the right. Now I want to complete the square. I want this to be some number so that this trinomial is a perfect square trinomial, meaning I'll have a perfect square for my first term, I'll have a perfect square for my last term, and twice the product of those square roots will equal my middle term, my linear term. Well, I don't want to just guess. I don't want to just start trying random perfect square numbers like 25 or 81 or 121. There is a method, and the method states to take 1/2 of b and square it. So in this problem, b is 4. If I take half of 4, I'll have 2. 2 squared is 4. But I can't just add 4 to the left because it's convenient. If I do that, I have to add 4 to the right as well. And now we can factor the left side. This becomes x plus 2, the quantity squared. The square root of x squared, the square root of 4. Multiply them and double it, you should get your middle term. If you don't, you've done something wrong. And on the right, we have 16. So now as we continue to solve by taking the square root, x plus 2 is plus or minus 4. Subtracting 2 on both sides, x is negative 2 plus or minus 4, which means x equals 2 or negative 6. Let's jump over to this last one, number 3. Again, sorting our terms looks something like this. Terms with x on the left, constant on the right. Half of 2 is 1. 1 squared is 1. So I'm going to add 1 to both sides. In fact, I'm going to do that in a different color just so that you see that we're doing that to both sides. And then I'm going to factor my left side. The square root of x squared is x. The square root of 1 is 1. 1 times x times 2 is 2x. And on the right side, I have negative 2. Taking the square root, we have x plus 1 equals plus or minus. Uh-oh, we have an imaginary number happening. The negative sign comes out and becomes an I, radical 2. And then finally, I subtract 1 on both sides. X is negative 1 plus or minus I, radical 2. So this quadratic, if I were to graph it, which I'll take a moment to graph it, you'll see that it does not cross the x-axis anywhere. X squared plus 2x plus 3, and graph. See, it does not cross, it does not have any real solutions, but it does have 2 imaginary solutions. Going back to the second problem, this one's a little bit more complicated because again we have this factor of 3. And when that happens, we need to get rid of that because we can't play our completing the square game when the leading coefficient isn't 1. So we're going to divide everything by 3. And that leaves me with x squared minus 2/3 x. Again, I'm going to move this negative 1/3 to the other side. Alright, now I know we've introduced a fraction, but we're still going to work with it just like we've been doing. We're still going to take half of b. Half of b means 1/2 of means times, and b is 2/3. Half of 2/3 is 1/3, and then I'll just square my answer to get 1/9. So I'm actually adding 1/9 to both sides. Using your calculator, as I just did, is not cheating. You can do that anytime if it will help you when you're trying to come up with the number we need to complete the square. Now I'm going to factor. The square root of x squared is x. The square root of 1/9 is 1/3, with a subtraction in the middle. Again, multiplying these and doubling it, I would get back to negative 2/3 x. That's my goal, is to get back to that, to check it. And on the right side, 1/3 plus 1/9 is 4/9. I'm going to take the square root of both sides now. X minus 1/3 is plus or minus. Now, the square root of 4/9 seems a little tricky, but that's just the square root of 4 over the square root of 9, which is 2/3. And then I'll add 1/3 to both sides. X is 1/3 plus 2/3, or 1/3 minus 2/3. Simplifying, this gives me 1 or negative 1/3. This is really helpful when we're trying to take something that's in standard form and get it into vertex form. The only difference is we can't really put this number on the other side because it's not equal to 0, it's equal to y. So instead, I'm going to group. I'm going to put my terms with variables in the parentheses, and right outside the parentheses will be just the number. I'm going to complete the square just like I was doing. Half of b is 3, squared makes 9. But since I'm doing it on the same side, whatever I do in the parentheses, I need to do the opposite outside the parentheses. Because inserting plus 9 minus 9, plus 9 minus 9 is just 0. I haven't changed the value of my function. Finally, right here, I can factor this, x plus 3, the quantity squared, and I can combine like terms. So now I am in vertex form. Vertex form of a quadratic looks like this, where HK is literally my vertex. So just looking at this, I can tell right where the vertex is going to be because it's in vertex form. Let's try one more. Again, I need to sort them. Terms that have variables and terms that do not have variables outside the parentheses. But I can't complete the square when my leading coefficient is not 1, so I'm going to factor that out. And you can check to make sure we did that correctly by distributing. Negative 2 times x squared is negative 2x squared. Negative 2 times negative 4x is positive 8x. Now I can complete the square. Now I can take half of negative 4, which is negative 2, squared is 4. And I'm going to subtract it outside. However, let's take a look at what I've really added. What I've really done is negative 2 times a positive 4. So far what I've really done, and this is where it gets confusing, I've really subtracted 8. So outside I need to add 8. That's very challenging to get the hang of. Normally, if we put a plus 4 here, we'd put a minus 4 here, but we have to account for the coefficient that's been factored out, because whatever goes into this parentheses automatically gets multiplied by the negative 2. So continuing to factor, the trinomial is now x minus 2, the quantity squared, and outside my like terms become plus 5. So this is my equation in vertex form.